So thank you, everybody, for coming. So first of all, let me just take a little poll. How many machine learning experts do we have here in the audience? OK, good. I'm not talking to you, unfortunately. I'm going to be talking to everybody else. And how many deep learning experts? Anybody who's not a machine learning expert, a deep learning expert somehow? OK, that's good. That would be interesting. So a little bit of background. My name is Carey Nachenberg. I am a fellow, technical fellow at Symantec Corporation. I'm an adjunct professor at UCLA, where I teach freshmen computer science. And I really enjoy that. And about a year ago, I had a new boss that joined on to Symantec, and he told me, you need to learn deep learning, and you need to bring deep learning into Symantec, which is where I do work full time. And so I said to myself, OK, this is a challenge. I'm not a mathematician. In fact, I'm horrible. I'm horrible with math. So I proceeded to learn deep learning by working with some friends. And I thought, this is a really interesting topic. Can I somehow present this to other people who don't necessarily have a deep math background so that you can understand deep learning as well? So my goal is not to go and give you lots of complex mathematics and so on, but rather to give you a gentle introduction with a little bit of math so you can have an intuitive understanding of what deep learning is all about. I am sure that I will offend some people in what I say because I'm going to be doing gross oversimplifications. And so I apologize in advance for those of you that are practitioners. Do me a favor, throw the tomatoes after I'm done. OK, so I call this deep learning for dummies because, again, this is meant for everybody, or people with a very, very limited math background. And I say like me because, frankly, I'm not a practitioner. Really, I am not doing a lot of machine learning at Symantec right now, frankly. OK, so what's the goal of this talk? To provide you with an intuitive, but not necessarily mathematical understanding of what deep learning is and why it works. Okay, and nobody's been able to do that for me. I read lots of papers online. They were very complex. A lot of them had typos in them. They were just very difficult to read. So I want to give you a very, very basic understanding of deep learning and why it works. As I said, I'm not an expert nor a mathematician. So you may actually challenge me, and I'll say, that's a really great question. Let's ask Andrew Ng. Okay, and then that'll be my answer in many cases. So what is deep learning? Well, deep learning is a type of machine learning. And that you might say, well, what is machine learning? Well, machine learning is a class of algorithms that can automatically learn concepts through automated analysis of large amounts of information and data. Okay, so we want to learn concepts. And then further, use those algorithms and use that understanding of the data to solve problems like recognizing a person's face or driving a car or understanding a spoken command. Thank you very much. Okay. So deep learning is a special type of machine learning. It's a subclass of machine learning where the machine learning, the deep learning system learns or discovers layers of increasingly complex abstract concepts about whatever it's looking at, whether that be a voice signal or an image, whatever it happens to be. So increasingly abstract concepts about the data it's trained upon. So for example, and this is taken from a Stanford paper, a deep learning system might be trained on a bunch of pixelated data, just raw black and white or color pixels. Okay? And that might be the input to the system. And then the system will identify one set of concepts that, hey, the images that I've been presented with actually have edges and curves and so on that are actually present in many different images that I've seen. Okay? So the deep learning system will learn this. And then it will actually take these regularities that it observes, these things that it sees across many of the images or pieces of data that's presented with, and it'll say, hey, wait a second, I can actually compose higher level concepts based on these simple things that I found within the data. And then from there, it can actually take these simple pieces and then say, ooh, I actually see combinations of these. And therefore, it can actually discover all of this on its own. So we're going to learn how, from the fundamentals, deep learning actually does this. So because deep learning algorithms discover these increasingly abstract concepts automatically, okay, traditional machine learning, that's why this is interesting. Okay, that's why deep learning is so exciting. So traditional machine learning approaches, when I first started doing some neural networks and decision trees way back when, you have to go and analyze the data yourself by hand. Okay, you have to go and say, oh, for instance, we use this for spam detection. Okay, we had to say, oh, these interesting keywords are used in spam, and these keywords are not used in spam, and then we have to identify those as features that we're going to use and say, well, if I see this and this, then it's probably not spam, and if I see this and this, it probably is spam. So we have to identify features. But the neat thing about deep learning is it discovers what's important automatically. It actually figures out what is relevant to the data that it's looking at. And it doesn't require humans to go and program that in. Whereas traditional machine learning approaches, we had to extract and identify the features ourselves in many cases. OK, now I'm going to be taking you from back in the 1920s to seminal work that was done and how that leads up to deep learning. And so you might say, when you start seeing the beginning of this talk, how does this relate to machine learning and processing images and understanding that there's a cat in an image? And the answer is just please bear with me. Try not to fall asleep. I'm going to show you a legend on the top of the slide. And we're going to start back in the 1920s. We're going to end with the human brain. And you'll see a little box around here. And that's how you know where we are within this talk. OK? So bear with me. There's a punchline. The punchline is right about there. OK? And we're going to get to it. And it's going to get a little bit of a build up there. OK? So there's a legend right there. You can see it at the top of the corner of the screen. And let's start. OK, so deep learning automatically is able to learn things about the data, find abstract concepts, multiple levels of abstract concepts in the information that it looks at. And it all goes back to the Ising model. So Ernst Ising was a physicist that was looking at magnetic dipoles and basically doing simulations of a bunch of atoms within a lattice. Okay, and he was working for Wilhelm Lenz, who actually came up with the Ising model. And I guess, I don't know why they call it the Ising model, not the Lenz model, but they were working together in 1922. And there we are. You can see we're just starting right there. And so what Ising was studying was, he was basically saying, can we model a series of atoms, which are either flipped up or down, okay, for magnetism, they flipped up or down, and how they interact with each other. Okay, and so what might the atoms look like? Well, you can see that some atoms are pointing up and some atoms are pointing down. Okay, and these atoms will vibrate over time according to some rules, some principles. Okay, and they actually have some connections in between themselves that will govern how they actually flip around and so on. And this is what he was doing. He was trying to model, if I have a bunch of particles, how will they interact with each other? Will there be, for instance, stasis? Will they, they get into a stable state, or will they flip-flop or oscillate and so on? Okay, now in the Ising model, there are weights in between these atoms. Okay, and you might think of these weights as a connection or strength in between, for instance, this atom and this atom. Okay, now each weight indicates how strongly the two atoms are correlated. And for instance, a high weight would indicate the two atoms should be pointing in the same direction. In fact, this would be an unstable state because a score of 99 would indicate these two atoms should really be pointing in the same direction, not opposite directions. Think of like a spring, and if you twist it, it wants to spring back into its original state. Okay, and so we would expect this atom to maybe flip like that. Okay, now a state, for instance, a weight of 1.0 would indicate, well, there's some correlation, but very little correlation between these atoms. And over time, we would expect these atoms to flip. Imagine if these were just random atoms and they're flipping. There's a cosmic ray that comes in. How would they flip over time and so on? That's what we're talking about here. And he was saying, how can we simulate this? How can we model this? Okay, and so you can see these atoms are definitely highly correlated. They're flipping a lot. This atom over here might flip randomly once in a while. Less correlation to this guy here. Okay, and oh, they flipped again. Now, some of the weights can be negative. So for instance, this weight here might be negative 50. And in fact, this would indicate that these two atoms are anti-correlated. In other words, they should be pointing in opposite directions. Okay, so in this case here, if these atoms were to flip, we'd probably see something like that, right? In other words, they're all going to stay in sync because these two atoms are highly correlated. These two atoms are anti-correlated, and they're going to flip back and forth. Okay, and so they're always going to be sort of opposite each other, generally. Okay, that's the probability that they're going to flip opposite each other. Now, the atoms experience pure pressure to flip as well. So for instance, let's imagine the weights were 500 and 300. So this atom's facing up, this atom's facing up. These are very, very strong interactions here. That would cause, all things being equal, a probabilistic, higher probabilistic chance that this atom is going to flip to face the same direction. Okay? However, that said, ultimately anything can happen. This is a probabilistic model. Anything can happen. This atom in the middle could just flip back. It's possible that it could just flip back and, oh, there it goes, and it flips opposite. Okay? So this is the Ising model. And basically, you can model any sort of set of atoms with different weights in between them. And what Ising was studying was lattice models. So he was basically studying, for instance, models of atoms in a square lattice with various weights. Now, let's look at this model. I've actually constructed a simulation, which I'll show you, which is a little happy face. And it's not exactly like this. I couldn't fit the whole model on the screen, so I'm showing you basically this is a happy face. And what I'm showing you here is that these atoms have higher correlations with each other. In other words, they have very high correlations. The ones on the sides have very low correlation, so they're going to flip-flop a lot more. And what I'm going to do is I'm going to just let these atoms sort of vibrate. I'm going to let them vibrate in simulation. We use a sigmoid function, if you know what that is, in order to go and decide whether they activate. There's a random number that's generated, and we basically let them flip and flop and vibrate based on these particular weights. So hold on one second, and hopefully you'll enjoy this. Okay, here we go. Let's make that bigger. What do you say? Oh, there we go. What do you know? Okay, so there you go. There's my happy face. Okay, now you notice that it's not actually showing a complete happy face. We see a nose there, and we're about to see probably a part of a mouth maybe showing up. Ooh, there's sort of some of the mouth. You can see it sort of standing out there. So the fact that I have these weights that are sort of tying atoms together doesn't mean they're necessarily going to flip in the same direction. Again, it's all probabilistic. Oh, there's a mouth. There's a nose. Let's see if we get an eye in there before it's, oh, there's an eye. And now notice the eye happens to be standing out. It happens to be, let's say, a positive spin versus the negative for the nose. Oop, there goes the nose standing out. You get the idea, okay? So it's just a simulation of atoms flipping up and down probabilistically according to the weights. Okay, so let's keep going here. All right, I'm already losing some people. I'm getting some sleepers. I take pictures of sleepers and then I post them on the internet. Okay, so let's take our Ising model. Now, every configuration of atoms, okay, and weights has a specific energy. Okay, so there's something called energy associated with these systems, and let's talk about the energy. Okay, so let's give each up-facing atom a score of +1, okay, and let's give each down-facing atom a score of -1. Okay, and this is part of the model. Now and between atoms, we're going to call these weights, as I said. So there we have weight 0, 1. Basically from x0 to x1, we have weight 0, 1. From x0 to x4, we have weight 0, 4, and so on. So you can see there are weights for each of these, between each of these atoms. Okay. Now, if we want, we can compute what's called the energy of the system here. In this case, we have 4 atoms, and we can compute, actually 5 atoms, and we can compute the energy of the system. And the energy of the system is simply as follows. We sum up that value, 1 times that weight, plus that value times that weight, and so on. Okay, so basically we're summing everything up. Let's see it. And we actually take the negative sign. So the energy is considered negative. Okay, so we have a negative sign there. So watch this. So in this case here, we take 1 times 1.0 plus 1 times -1 times -50. Okay, and then 1 times -1 times 1.0, and 1 times 99. We sum them all up, and we take the negative of that. Okay, so there's our energy function. And what we find is, and based on the theory, low energy configurations are those in which atoms are connected and basically pointing in the same direction when they have high positive high positive weights. Okay, so in this case here, for instance, notice that these two atoms are aligned. Okay, these two are aligned, so that's good. That's actually a negative energy state. It's a very low energy state. That's the way it wants to be. It doesn't want to flip from that state. It's actually good. Okay, and similarly, if I have atoms that are anti-aligned or anti-correlated, and they have a negative weight, that's also a low energy state. The system likes to be in the state. It actually likes to be in the state. Okay, and these configurations tend to be more stable. Okay, now high energy configuration, that's a low energy configuration. A high energy configuration is one in which atoms that have a high positive weight are actually anti-correlated. So look, we have this here, 2 atoms that are actually facing opposite directions, and yet they have a high positive weight. Or here we have 2 atoms facing the same direction with a negative weight. These would be anti-correlated. And this is an unstable system. These atoms, just like a spring that you've sort of turned the wrong way, is going to want to spring back the way it started. Okay, so pairs of atoms with positive weights tend to be anti-aligned in a high energy system. These are aligned if they have a negative weight. This is also high energy. And what you will see is in this type of system that you're going to actually have a flip, and it's going to try to go into a low energy state, and you'll go from a +149, for instance, to a -149. And that's the system will naturally do that probabilistically. It's going to go over time and vibrate to a lower energy state. Okay, so let's consider an Ising model with 3 atoms. Okay, now just 3 atoms, 1, 2, 3. There are 3 possible states of those atoms. It can be up, 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 down, up, and so on. Right, just the binary states. So here we have 3 atoms, all up. Down, up, 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 down, up, and so on. And there are the 8 states. And here we see weights of -50 and 99. So imagine these 3 atoms can vibrate through these 8 different possible states. Okay, they can be in any of these 8 different possible states. Okay, now, here are the energies of these 3 atoms. Okay, so if the atoms are facing up, 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 the energy would be -49. A negative energy, which is good. It means it's reasonably stable, but not nearly as stable as this configuration here with an energy of -149, where the atoms are more, again, sort of the way they want to be. Okay, now if we take this system here, and we started it up, 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 and we just let it vibrate. In other words, it's going to vibrate, cosmic rays are going to hit it, we're going to simulate this. What we'll find is that this first configuration, x1, up, 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 okay, it occurred once. Now let's let it vibrate and see what it does. Oops, well that went down. That was down, up, up, and then that was x2, and then x8, configuration x8 came about, and we let it vibrate some more, and x2 happened again, and so on. And if we let this vibrate over time, we're going to build a histogram of every possible configuration this can be in. Now, with just 3 atoms, there are only 8 possible configurations, and we can actually watch this over time for 1,000,000 iterations, and we're going to see a nice histogram of sort of what state it's going to stay in. If you had 1,000,000 atoms, there would be 2 to the millionth states. Okay? So it would be very difficult to actually measure this empirically, although you could try. That would be sort of interesting. But in reality, we're just measuring this for just 8 different states for 3 atoms. Okay? But in a real system, like for instance, one you might use to learn, with millions of atoms, you really can't measure this. Okay? Now, this histogram here, okay, what you notice is that low energy configurations like this 149 where the atoms with a positive weight are facing the same direction and negative weights are facing the opposite direction, they tend to occur more frequently in our histogram, which makes sense, right? They are lower energy, we're more likely to vibrate to them. And similarly, high energy configurations with a very high energy, are less likely to occur. Not infinite, they're going to occur occasionally. I mean, it's possible a cosmic ray will hit something and you're going to vibrate to that state. In this case here, we didn't vibrate with our little limited sampling, but we probably would, but just at much lower frequency. Okay, and that's as expected. Okay, now the probability of vibrating to a given configuration x sub I to a configuration x2, like for instance down, up, up, for example, is predicted by this formula. Okay, so the probability of vibrating to x sub I, whether it be x5 or x7, okay, is e, obviously 2.71, right, to the negative energy of that state. Okay, so we know the energies of these things, so it could be e to the minus 149 over the sum of all the energies for all the possible states. Now, if I only have 8 possible states, it's possible to empirically, compute exactly what that denominator is. But in most cases, if you have 1,000,000 atoms, you're not going to be able to compute that denominator. Okay, so we're going to have to do this mathematically. But in this case, I literally could add up e to the that, e to the minus that, plus e to the minus that, plus e to the minus that, and so on to get the denominator. And I can now compute the probability that any particular state will come up. Okay? So the more negative, if you notice, x sub i's energy, the higher the numerator will be, okay? And therefore, the higher the probability of the configuration actually popping up more often. Hopefully that makes sense. Okay, and so now we could, if we wanted to empirically sort of measure the probability of each of these configurations popping up on, in our 3-atom series. Okay, now for simplicity for the rest of the talk, I'm going to call this value here, e to the minus energy x sub I of weights. Okay, and by the way, the energy again includes the direction these atoms are facing and the weight values. That's what x sub I and w are. Okay, we're going to call that E energy for now. And so we can actually write this equation in a simpler way of saying the probability that the system vibrates to one of these 8 configurations is the E energy of that configuration, like 149, divided by the sum of all E energies. Okay, so hopefully that makes sense. We can continue. And by the way, if you've heard of it, this is called the Boltzmann distribution. Boltzmann, I believe, was around in, I think, 1868, and Boltzmann was studying, basically, if you have a system with a bunch of moving parts, how often will that system be in any particular state? How often will 2 atoms be up versus 1 down and 1 up, and so on? And that's basically the Boltzmann distribution. Okay, so this is the distribution for this set of 8 atoms. Okay, now, what if instead of having weights on a plane, so in other words, a 2D lattice, like we saw with a happy face, what if instead we had weights between 2 adjacent planes? Okay, so this is what we had before. We had positive and negative weights with atoms of various spins up and down. And what if we switch from that 1-dimensional, or rather 2-dimensional approach to one that's a 3-dimensional approach? We have a visible plane, there it is, okay, and a hidden plane. Okay, so now we have a visible section and a hidden section. Think of this plane like a touch screen. Not only can it display something, in other words, the the direction of the atoms. Think of, for instance, an up direction as being an on pixel and a down direction being an off pixel, for example. Okay, but it can also potentially influence. In other words, if you touch it, you might influence the state of the bottom plane. Okay, so the bottom plane can influence the top can influence the bottom. Now, in this case, you don't have weights in between items on the top plane, and you don't have weights in between items on the bottom plane, but you have weights between the top and bottom plane only. Okay, only. Okay, so for instance, that neuron, or let's call it a neuron right now, because actually we're going to go there, but that, that node right there, or neuron right there, is connected to these 4 nodes here with a negative weight there and positive weights there and so on. Okay, and for example, that node right there, that atom right there, is connected by those weights. And in general, every atom on this plane is connected to every atom on that plane. Okay, so this is a 3D Ising model. Now, atoms on each plane are now only influenced by atoms on the other plane. In other words, this atom, no matter what its value, will never influence this atom directly because there's no direct connection here. There's no force. There's no spring between these 2 atoms. Okay, so for example, if this atom here, for instance, happened to flip, okay, the only impact would be on these atoms here, not on the atoms that surround it. And these atoms might flip in response to that atom flipping. Okay, and similarly, if this atom here were to flip, for example, then the only atoms that would be impacted would be atoms up here, not atoms down here. And for instance, we might see these atoms flip. Okay, so the connections are between the planes, not intraplane. Okay. Now, in such a model, energy is computed a bit differently, but it's analogous. Okay, and the energy is now basically the following. Okay, double summation. Okay, and basically what we're doing is we're taking every visible atom and every hidden atom, and we're saying for each visible to hidden combination and the weight between them, we're going to sum them all up. Okay, so let's give you an example here. For instance, to compute the energy, we can take V1. There's V1. There's a visible atom 1. Okay, there's hidden 1. There's hidden atom number 1. And there's a weight between visible and hidden atoms 1. Okay, so there's weight 1, 1. And we can basically multiply those together and sum that up with V1H2. So we'll take visible 1 and hidden 2. Okay, and the weight between 1 and 2, we'll sum that up and so on. Okay, so now we can compute, if you will, the energy of this entire system. Okay, we can do this one. There's V9, and there's H4, visible to hidden, and there we go. We take the weight 9, 4, and we would sum that up. Now, just like before, if we have a visible atom and a hidden atom that are connected by a weight, okay, and it's a positive weight, okay, and they're facing the same direction, notice both facing up, that would be low energy. That's a low energy state, okay? And similarly, for instance, if we had a visible and a hidden atom facing in opposite directions, okay, that would be with a negative weight, that would also be a low energy state. So these are the low energy states. They're just between visible and hidden layers now. And as before, configurations with lower energy, okay, are going to occur with higher probability than those with high energy. And when I say configurations, I mean of all the atoms, both the visible and the hidden planes, because now they're dependent on each other, okay? So if we want to compute the energy of a configuration, once we find that, we can also find the probability of a configuration occurring. So for instance, we might ask, what's the probability of the system vibrating to a particular 3D configuration? So for instance, what's the probability of this system vibrating to up, up, down, up, up, down, down, up, up, down, up? Okay, that we can ask that question, and we can actually compute that by computing the probabilities using the energy model we talked about earlier. Okay, and so the answer to this is the E energy of the configuration, e to the negative energy that we talked about before of the whole configuration, divided by the total E energy across all possible configurations. And if we, in this case here, we have 9 and 4, 13 atoms, so 2 to the 13th power, total configurations. We could sum up all the E energies, and that's how we figure out the likelihood of any particular state this would be in. And we can also compute the probability of the system vibrating to a particular visual configuration. Okay, now how do we do that? What do I mean by that? We can say, what are the odds that the system will vibrate to exactly that visible state, okay, irrespective of what that hidden layer is? We don't care what that hidden layer is. We just want to know what's on the touch screen, what's on the monitor. That's what we want to ask. What's the probability of vibrating to up, up, down, up, down, down? Okay, we can ask that. And irrespective of what those atoms look like. And we can compute that as well. And the way we do that is obvious. Basically, we say, okay, the probability of this configuration here, okay, displaying the visible configuration V, is the probability that we display this, given these are all facing down, plus the probability of displaying this, given these are all down and 1 is up, and so on and so on. We can go through all the combinations of all those bottom atoms and sum them all up, and that's the probability of displaying the top visual display there. Okay, so you get the idea. We can compute the odds that this system will vibrate to any configuration, like of both top and bottom, or we can compute the odds that the top only, the visible plane, will vibrate to some configuration, irrespective of what the bottom looks like. Okay, so just as with our 2D Ising model, we can pick weights to bias certain configurations of atoms. So for instance, remember I showed you the happy face? I picked some weights. Well, we can do that as well. So for instance, we can positively connect upper left hidden atoms, okay? This atom right here, let's forget about these for the time being. Let's connect this guy here to the first column. Okay, and we'll connect it with green means positive correlation, so high positive weights. We can connect this to the third column with green lines, meaning high positive weights. And if hopefully you're not colorblind, we could also connect it to the even columns with negative weights. So this is red, that's a red color, and we could do it there with a red color. And so there'd be negative weights for these. So now we would expect, okay, that that atom would be positively correlated with those two columns. In other words, it's going to flip in the same direction together. And we would expect that that atom would be negatively correlated, in other words, flip in the opposite direction for those two columns. Hopefully makes sense. Okay, and so we'd expect our top layer to either be stripes. In other words, first row all the way up if this is up, third row all the way up if this is up, and then the other one's down and so on. So let's see what happens there. Oh, they're vibrating. Oh, look at that. That one's aligned with that one, that row and that row, or that column and that column. That's anti-aligned. If we let it flip again, oop, oh, look, they're still aligned, still aligned. These are sort of anti-aligned. And we let it flip again. And of course, it's not perfect. Look at that. That atom there decided to get out of line. It's not really playing ball, but that's okay. That's possible. Okay, and so on. So these are going to keep flipping and so on, and they're going to generally be aligned because of the positive correlations. Now, why is this the case? Why are we seeing this? Well, let's imagine we have our hidden atom here, and we're only dealing with one hidden atom. If the hidden atom just happens to randomly flip up, okay, let's imagine it happens to randomly flip up, okay, oop, there it goes, it flipped. Okay, it is going to influence, okay, positively correlated items in the visible plane, and they're going to flip up as well, or they're going to have a higher probability of flipping up because they have positive connections. They have springs that are sort of in the same direction, right? So they're going to flip up like that. Okay, now. And similarly, let's just imagine that atoms on the top plane happen to randomly get hit by cosmic rays, and they happen to flip around like that. Watch, okay? So maybe all three of them are flipping down. Well, those atoms will have a strong effect on the bottom hidden atom as well. And so what we would expect to see is that if these guys flip, they're going to cause him to flip because most of them are flipping in the same direction, and he's going to go and say, well, I don't want to be in an opposite direction. I want to be aligned. I have peer pressure here, okay? And so this will further reinforce alignment on the plane. So we're going to have alignment between the two planes. If this atom's up, they're going to tend to be up. If this atom's down, they're going to tend to be down. If these happen to randomly flip, most of them over 50% up, then he's going to randomly flip up as well, and so forth, okay? So they're going to be aligned with each other. So what this is a semi-stable system. It's or maybe a bistable system, right? In this case, it's bistable. They're either all going to be aligned up or all aligned down most of the time. Occasionally, they'll go and flip opposite each other. Okay? So this creates a self-reinforcing set of stable configurations. Now, in fact, we say that our 3D Ising model that we show here is a generative model. And for those of you that don't know what a generative model is, we call it generative because if we allow the system to vibrate, so this atom flips wherever it would flip, and these atoms respond because they're connected by those weights, and they flip and so on, then we're going to naturally tend to generate patterns on the visible surface that are based on the specific weights connecting the two planes. So whatever those weights are, they're going to influence or bias the system to vibrate in a certain way. Okay? And in fact, we would expect a Boltzmann distribution, okay, with two peaks. Okay? The first peak would be odd columns on, up, so odd up and even down. Okay? The second peak would be even up, so even up and odd down. Because if this guy is facing down, then we're going to have odd down, even up. And if this guy is facing up, we're going to have odd up, even down. Hopefully that makes sense. Okay? So we would expect this to be a bistable, configuration where we could actually go and flip-flop into either of these. And it might be possible that we actually flip-flop into some other state as well that's along, it's somewhat close. And so when left to vibrate, this system is going to go from sort of even odd, up, down, or down, up, back and forth, back and forth. This is going to sort of vibrate between these states with high probability. And it's almost as if it's daydreaming. The system is daydreaming because it's reproducing what it knows. It's actually going into these states over and over again that it knows. And so think about when you daydream, you think about the things you know. You think about the images you've seen before, right? You're just basically going. You have neural weights. And I'm drawing the analogy for a reason. You have neural weights in your brain, and those will influence how you think about, what images you see, and so on. And it's analogous in some ways, we think. So talking about daydreaming, let's see an example. So here's a demo, and there are 5 atoms on the bottom, and there's a visible plane. So here's a visible plane, your touch screen. Here are the 5 hidden atoms. And I'm going to go and connect manually, I'm going to do this on my own, each atom to various atoms here on the top visible plane. So I'm going to connect hidden atom number 1 to those sets of atoms right there. Okay, so I'm going to basically have strong positive weight connections between that atom and those sets of atoms. I'm going to have the next atom connecting to that middle one, a nose. The next atom connecting to part of a mouth. The next atom connecting to part of a happy face, sort of grin. And the next atom connecting to part of a sad face. Let's see what happens. Okay, so here we go. Oh, look at that. Look at that happy face. Oh, look at that. Now he's neither happy nor sad. Okay, so this is just the random vibration of the system. A pound sign is an atom that's facing up. Okay, an empty sign, an empty space is an atom facing down. And you can see the system is vibrating. I think it's going to go negative. It's going to go through a phase change where the eyes are actually going to become negative. Let's see if that happens. Maybe not. Come on, let's see. Let's see. Maybe the nose. So you can see it's very, oh, I guess not. Okay. Well, anyway, you get the idea. We can influence common states of the system so that they basically occur much more frequently. Now notice, that system of atoms could have turned into a cat. It's just very, very unlikely because we have these weights that really influence it or bias it to become a happy face or a sad face. Okay, so, oops. Okay, so by manually adjusting the weights, we did it manually, I actually did it by hand. Between the 2 planes, we can basically bias the distribution of what images are going to show up. We can cause it to daydream in a manner that makes me happy. Okay, now, there was an aha moment, okay, where the 3D Ising model becomes the restricted Boltzmann machine. So basically, okay, here we have the Ising guys back in the early 1920s, and they're studying how these system of atoms vibrate and all the relations between them and so on, and what the energy states are. And then 2 guys come around, and there are lots of people involved. So don't tell me, or you can tell me afterwards that hey, these weren't really the guys. There were other guys. You know, there's a Hopfield and all these other people who are involved in this, and we have to give them credit. But let's talk about Jeffrey Hinton and Terry Nachenberg, who really sort of launched this field, I would argue. And they had this idea, and they said, hey, let's use a simulation of an Ising model. Let's use an Ising model simulation on a computer to encode memories. Let's teach these atoms to learn about memories. Okay, so in the early 80s, Hinton and Sejnowski started experimenting with 3D Ising models. So remember the 2 planes we just talked about. And they called them, or what they're called, restricted Boltzmann machines, or RBMs. So maybe you've heard of an RBM. It's really just a 2-plane set of Ising model with connections between the 2 planes, but not between each plane, not intraplane. And their goal was to come up with an algorithm that could take a blank RBM network, so just all random weights, you know, all values of 1 weights, let's say. Okay, so random weights. And then teach the network, by modifying its weights, how to encode a memory. Okay, so it would reproduce, for instance, a happy face image. So instead of manually typing in weights like I did, where I actually said between here and here there's a plus 100 weight, what they did is they said, can we somehow learn automatically how to reproduce a happy face? Okay? So if allowed to vibrate, once they learn these weights, notice they're green and red now, the RBM would vibrate up this encoded image more frequently than other images. That was our goal. Okay, so I'm going to show you a possible communication between the 2 of them. So Hinton says, Terry, I wonder if we can train a 3D Ising model to remember a picture. And then Sejnowski says, to remember a picture? This is probably how it happened, right? And then Terry says, or Hinton says, I want to be able to pick an arbitrary image. And he goes, oh, there's my image. He sort of dreams it in a bubble, okay? And he says, and then find some automated way to pick the weights of the Ising model so that when it vibrates, it shows my picture more often than it shows other pictures. Okay, so it vibrates more often to my image rather than other images. Okay, and he says, I see. Well, as we know, Ising models naturally vibrate to low energy configurations, right? They vibrate, they will tend to vibrate to configurations that are more low energy, or lower energy, okay? And so all we need to do is pick a set of weights that causes our desired image to have as low an energy as possible, okay? So if we pick a set of weights such that when those weights are present and when an image is present, the image we desire, the system's energy is very low, that image is going to show up on that visible plane more often. Okay? And so he says, right, then our Ising model will naturally vibrate more often to our image. We'll actually train it, we'll give it memories. Okay? So they use what's called a gradient descent algorithm, which many people spend copious dissertations on, which we won't talk about. But it's a very interesting algorithm, or set of algorithms that solve a problem. And what this problem is they figure out the right set of weights given something they need to optimize for. Okay? So what these guys wanted to do is they said, okay, here we have our 3D Ising model. We have to determine the weights between the visible layer and the hidden layer such that the energy for this image is as low as possible, and this image will likely vibrate up. So they take this in, they stick it in that black box, okay, and let it run. See the gears are running. It's very exciting. It almost looked like that, I think, when it really happened there. And then it comes out with a set of weights, positive and negative weights, okay, that we will use in order to connect the visible and hidden layers. Okay? Okay. Now the resulting Ising model is a generative model. Okay? So what does this mean? Again, once we've computed these weights with our gradient descent algorithm, if we let the system vibrate, an atom goes on here, an atom goes off here, on here, off here, vibrate, 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 this called Gibbs sampling, what will happen is that this image will more probably show up on the visible platform or plane than other images. Okay? That's what they've tried to do. Okay? And ultimately, why is that the case? Because these weights create a low energy state when this image is actually displayed on the visible plane. Okay? So these weights were chosen such that when that image is shown, that is the lowest energy state, or one of the lower energy states of the system. Okay. So if you remember our Boltzmann distribution, where we basically did the histogram and we counted how often things happened, how often we were in various states of 3 atoms, for instance, okay, we can compute a Boltzmann distribution for these atoms as well. Okay, and basically what we're going to do is we say, okay, this image, once we've run our gradient descent algorithm, should occur more frequently than any other image, ideally. Okay? In other words, if you're letting the system vibrate, the probability, this is a probability distribution, is that it's going to vibrate to that image more frequently than other images. Now, it's really not a bell curve like this, because in the case of, let's say, 100 atoms, there are 2 to the 100 states, right? These atoms can be in 2 to the 100 states, off, 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 on, blah, 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 right? So this can be in many, many different states. So it's probably going to be a very flat curve with the middle in this image being more probable than other images, but still very, very unlikely. Okay? Now this image here, which is maybe with a little part of the eye missing, is going to probably go over there on the curve. In other words, it's going to occur more frequently than other images, but it's less frequently than the image we were trained on. And here's another image with part of the mouth missing and a spurious atom on there, and that would probably be over there, let's say. And so you can see we're going to vibrate more frequently to things that look like our happy face, with the happy face being the most probable once we've run through a gradient descent algorithm. And then things that look totally unlike what we trained on are going to have a very low probability of occurring, or lower probability of occurring. Okay? And this is because the weights are picked in order to have a low energy when this item is present, when this visible configuration is present. Okay. So what is actually happening to our weights during the gradient descent algorithm? Okay. Well, let's imagine for a moment that we only have a single hidden node, a single hidden atom. And we want to train to learn this training image. We want to vibrate to that training image. Well, as you might expect, our gradient descent algorithm would like positive weights, okay, positive weights, positive correlation, to all atoms that need to be on in the image. Okay, so for instance, that atom is going to have positive green weights to every atom that we want to be on, and we think that the gradient descent algorithm will do that. It's going to actually, that's what it's going to end up doing. Okay, and we'll have negative weights to every atom that should be off. And this will be a bistable system, right? In other words, it's going to flip positive or negative. Everything, the happy face is going to be on, or it's going to be off, and the background will be, on or off. Okay. So this will bias vibration of the system to configurations representing resembling the trained image. And why is that? Because in those random cases where this atom flips on, right, what's going to happen is it's going to influence the atoms on the visible plane, and they're going to flip on too. And similarly, if, for instance, the visible plane happens to go into a configuration, okay, like that, which is sort of close to a happy face, but not quite, that's going to cause activation of the hidden atom, probably. In other words, it's going to push that atom to go in a line. And that atom aligning and going in the right direction is then further going to push this towards its desired state. So what we're going to do is it's almost like we're rolling a marble down a hill. We're going to go and get closer and closer to our desired image, because anything close to our desired image activates this atom, which then activates the rest of the network to get closer and so on. OK. So they did that, and they said, OK, we can go and train our Ising model to vibrate to a particular image more often than not. And they said, and then Hinton said, what did Hinton say? OK, we know how to go and train an Ising model to learn a single image. OK. He says, but what about training it on 3 images or 1,000,000 images? Is there some way we can take that Ising model, the 2 planes, the 3D Ising model, and have it vibrate more frequently to 3 different images than to any other image that we haven't trained on? And he says, why not? Instead of using gradient descent, okay, to basically optimize for a single image, why don't we use it to optimize for multiple low energy states? So right now we're using it to optimize for 1 image. Let's use it to discover a set of weights that create multiple low energy states. So we'd actually have 3, right? In other words, this is higher probability than things around it. This is higher probability than things around it, and so on. And you can actually use a gradient descent algorithm or a gradient descent algorithm to actually do this. So now we can actually make our Ising model so that as it vibrates, there's a higher probability it will vibrate to one of these 3 states and other states. Okay, there's still some probability it will vibrate to other states as well. Okay, so he then says, you're saying it's possible to find a single set of weights that will create multiple such low energy points? And he says that's correct. If you have enough atoms or weights, the system can represent multiple low energy states, right? 3 in this case low energy states, or 1,000,000 for instance. Okay, so intuitively, how does this gradient descent algorithm, and this is where you really need to pay attention. If you were sleeping, wake up. Discover, see, look, we're getting to the exciting part here. Okay, how does it discover a combination of weights that creates multiple low energy states? That's the question. This is the fundamental question behind deep learning in my mind, and we'll see why it's relevant. Okay, so here we have training image 1, training image 2, training image 3. Wake up. Okay, now notice that some atoms in our 3 training images, and there might be 1,000,000 training images, but let's just imagine we have 3. Notice that some atoms in our training images are actually consistently on across all of our images. Okay, so let's go and just flash them up there. Okay, well, look at the eye atoms. Notice that in the first 2 training images, the eyes are the same. In the third image, even those 2, the diagonals are on in the third image, right? In other words, there are consistent atoms that are actually on across multiple training images. Okay, so all 3 images have those 2 atoms on. All 3 images have those 2 atoms on. All 3 images have those 4 atoms on, and so on. Make sense? Okay, so our gradient descent algorithm identifies these regularities. A regularity being consistency across multiple training inputs, multiple images, for instance. You know, the eyes are the same across multiple images. Okay. And what it does is it ties them with strong positive weights to hidden atoms. So it'll pick some hidden atom. We don't know how it does it, but in other words, there's in order to minimize the energy, it's going to pick, let's say, that hidden atom. And it's going to say, because these atoms were on across all of my training images, or many of my training images, I'm going to associate this hidden atom here to those visible atoms there. And similarly, it might pick that hidden atom there and associate it with those 2 visible atoms there, because they are on frequently. Okay, and then it might associate that atom to the node, or the nose atoms there. Okay, and it's going to similarly tie atoms that are off frequently across multiple images with negative weights. So, for instance, it might tie everything, for instance, to all the things that shouldn't be on. That basically this pixel, this atom, is off in every single image. It's going to tie those to an atom with negative weights, for instance. Okay, now why would it do this? Why would it do this? Okay, now associating a positive weight between a hidden atom, for instance, that atom there, okay, and 1 or more visible atoms, so here is our visible plane, that are frequently on, okay? So notice these 2 atoms are on here, okay, they're on there, and they're on there. Those same 2 atoms are on across all the images. Associating a hidden atom with those 2 atoms that are consistently on, or on more often, means that anytime the hidden atom activates, watch it activate, there it flashes, okay? Anytime it activates, there's a good chance, or a better chance, that it'll also activate those visible atoms, right? In other words, if this activates and it's positively correlated with those visible atoms, they're going to activate as well, okay? And guess what? Those atoms are useful in reconstructing our training image, right? In other words, they're useful in reconstructing all 3 training images. If those 2 atoms activate, we're getting much closer to one of our desired images actually vibrating up onto the surface. That make sense? Raise your hand if that makes sense. Maybe you want me to repeat that. Yeah? No? We're good. Okay. Okay. So similarly, for instance, okay, so if this atom activates, it's going to activate those two visible atoms. And by the way, that actually is very useful because those visible atoms are present in all of my images I wanted to train on. And so therefore, there's a higher probability that one of those three images will show up than if I didn't activate those common atoms. Okay? So this increases the odds that one of my trained images is going to vibrate up on the visible surface. So the gradient descent process, this process of figuring out the weights for multiple training inputs, identifies regularities, common clusters of activated visible atoms, okay, common clusters of activated visible atoms that are across multiple training inputs, multiple training images, and it ties them with positive weights to our hidden atoms. Okay, and associates those with stronger weights to the various hidden atoms. So for example, this hidden atom is associated, potentially, with parts of eyes that are frequently required for us to display our images. And the gradient descent algorithm will figure this out. It'll say, ooh, if I basically pick that atom and I tie it with strong weights to those, there's a higher probability, the lower energy of the entire system, that part of the eye actually showing up, which gets us closer to our overall images showing up. Okay? Or similarly, this hidden atom might be tied to, for instance, parts of noses, or the nose itself if it's very simple. Okay? And why is this? Well, guess what? If this atom activates, then there's a high probability the nose will activate, and that's what we want because we want noses to activate because all of our training inputs have noses. Okay? So the gradient descent algorithm will naturally find, okay, these regularities that will cause a higher probability of certain elements of the picture showing up and associate them with hidden atoms. And in practice, these identified regularities will be very simple. They're not going to be an entire nose. They're not going to be an entire eye, but they might be an edge. They might be a little curve. Okay? They're going to be very simple. And it's this exploitation of regularities that causes our RBM to vibrate more often to its learned images than to non-learned images. Because basically, that's what, we identify the things that are frequently seen across multiple images, we reinforce those positively, and we're more likely to vibrate to those. Okay, so in essence, our RBM is gaining an intuitive understanding of the images it's been trained on. Now, let me give you an analogy here because maybe I'm still a little bit, maybe it's not making too much sense, or maybe it is, I don't know. Imagine if I have a chef, and the chef is very susceptible to brainwashing. And I just, I'm feeling like some Italian dish. Okay, and I know most Italian dishes have some tomato sauce in them. So imagine if I put some tomato sauce on the counter in the kitchen, and I just sort of watch the chef, and he goes, "Oh, tomato sauce. Maybe I should make an Italian dish." Right? That's what we're talking about here. We're identifying common elements of many different Italian dishes, and we say, "Ooh, that's tomato sauce," and we say, "Hey, let's go and bias the probability that we're going to have an Italian dish made because we're putting tomato sauce on the counter." Similarly, there's your tomato sauce, there's your Italian dish, okay? Okay, so our RBM is learning what features are common across the universe of images it's seen. They're actually, this process where we use gradient descent is actually saying, ooh, tomato sauce is actually common to all these Italian dishes. I'm going to put tomato sauce on the table. That's going to be hidden neuron number 1. And that's going to bias production more of Italian dishes. Now, here's where things get really interesting. Because once we've trained our RBM on a bunch of images, okay, what would happen if we were to manually flip our visible atoms to one of our training images and hold them steady? So let's go flip. We already have the weights here. So we computed all the weights, or we did it automatically. By the way, for our 3 images, or a million, or whatever we wanted to do. And we then basically flip up the atoms that are in yellow and flip down every other atom. Okay, so we're basically configuring that visible plane so it's in a certain configuration. And we clamp it there. We say, you're not allowed to vibrate. Okay? No vibration. But we allow the hidden atoms to vibrate. Okay? Now, as you would expect, the hidden atoms are going to go and vibrate, and they're going to activate based on, hey, look at that. There's a ratatouille or whatever, so therefore we're going to go and vibrate that atom on because there's our pasta or tomato sauce node. Okay? So what's going to happen is a set of atoms in the hidden layer are going to vibrate on based on activation from the visible layer. Make sense? Okay. So in essence, the resulting hidden atom configuration, you can think of it as a code that describes a set of regularities that were found in the visible image. Okay? So, for instance, if this atom turned on, that would mean that the image appears to have part of a left eye. Ooh, interesting. Okay, well that's interesting. And for instance, if this atom turns on, that means it appears to have a nose. Okay? So basically, when we clamp this and activate this, this tells us what regularities, what commonalities occurred within those images. Okay? And this appears to have part of a right eye, for instance. So the hidden atom configuration therefore represents a high-level description, if you will, of the original image. It is sort of a description of the original image. Okay? Okay, so let's take our trained RBM, that two-layer system, the Ising model. Okay? So we have all our weights. We computed those weights for our 3 images. And let's take each of our training images. Okay? Our 3, and there could be a million, but let's just take 3 now. And let's go and clamp them onto the visible surface. So we're going to clamp that happy face and that happy face with a full eye. And then we're going to clamp the other happy face, the sad face actually, on there. And we're going to allow the hidden layers to react as they would react. Okay? So in other words, activate whatever they would activate based on what they see in the visible layer. Okay? So now we have 3 high-level descriptions of each original image. Okay? Okay? And we can actually gather those up. So let's do something wacky, something crazy and wacky. Okay? Let's create a second restricted Boltzmann machine. A new restricted Boltzmann machine that's completely blank. Okay, there it is. Has a bunch of gray weights. They're all random weights. Okay? And let's use gradient descent. Let's use that algorithm we talked about. And let's pump in these high-level descriptions of those images. The one that says, oh, there's part of an eye, and there's part of a mouth, and there's part of a nose. Let's pump those in and train a new restricted Boltzmann machine. Okay? So you can pump those in and train and identify a set of weights for this RBM. Okay, so we'll pump those in. We're going to use the gradient descent algorithm with the gears that we talked about earlier. Okay, pump those in, pump those in. And then we're going to learn the weights so that this restricted Boltzmann machine vibrates to these 3 visible configurations more often than other configurations. Make sense? In other words, once you train this RBM to vibrate, it's going to vibrate to one of these 3 images as opposed to other random images because that's what we taught it to do. Okay? So these specific configurations of atoms are going to vibrate more commonly, more often, on the visible plane. And as before, to do this, we need to find the regularities across these images. Right? In other words, the restricted Boltzmann machine, when we train it, fundamentally, the way that we cause it to vibrate to these items more than other items is by finding the common regularities in these sequences and we want to go and associate them with hidden atoms that are going to cause those things to pop up more frequently. Okay? So what does this look like? Okay? So what we have here is when we train our new RBM, its visible atoms don't represent raw dots. In other words, these atoms here don't represent the raw dots in a pixelated display like we had in our original example. These represent, looks like there's an eye, looks like there's a right eye, looks like there's a nose, and so on, not raw pixels of black and white pixels, right? So as we learned, these atoms represent more abstract concepts, right? That, for instance, that atom there might represent part of a left eye. Okay? And so therefore, that atom there now represents part of a left eye. And that atom there might represent part of a nose, or, for instance. Okay? And that atom there, therefore, represents part of a nose. So when we train our second RBM, when we use gradient descent, what happens is that it will discover regularities in these inputs, not in the original set of inputs, but in these inputs, and it will associate those with hidden atoms. And this will discover higher order relationships. It'll say, ooh, all 3 images have that left atom on. I better cause that to activate. That means all of my images have an eye, for instance. Okay? So, for instance, this atom might activate when an image has 2 eyes. Okay? And so, for instance, it might be tied to that atom there, which is associated with right eyes, and that atom there, which is associated with left eyes. And now, if this goes on, well, then it turns both those on because all the images we saw had 2 eyes. And so it figures that out, and it actually encodes that in this RBM. So there's an interesting intuition because we can repeat this process over and over. Every time we add an RBM, we can train a new RBM. Okay, it's going to learn successive levels of abstraction about the images or inputs that it's been trained on. Okay, so for instance, here we had a black and white screen, right? We had images which were pixels were either on or off. Okay, at this layer, we learned that we were able to represent simple facial features like a part of an eye, and a hidden atom might be connected via a positive weight to a part of an eye that was common across many of the images, right? At this layer, maybe this represents facial components. In other words, 2 eyes together, okay, or an eye and a nose, for instance. And at this layer here, we might actually represent entire faces, Okay? So basically, for example, when that and that activate, that might represent a happy face with hair, okay? Which would activate, for instance, this atom here and this atom here, which would activate these atoms and so on. Okay? And so we can actually go 6, 7, 8, 10 levels deep if we need to and discover increasing regularities about the data at increasing levels of conceptual what's the right word? Abstraction. Okay? So for instance, these atoms might be a sad girl's face. Okay, and in fact, and here we can see from Andrew, who's probably not here right now, but some of his research, he starts by pumping in on this layer here a black and white image, maybe with some grayscale. This is what this layer detects. It detects simple edges because those edges are present in many different images. It says, ooh, look at that. There's a regularity. If I go and activate this, I'm going to see this. I'm going to cause this to occur more frequently on my visible plane if I vibrate. Here we combine these edges to get even more abstract concepts, like ooh. These are actually associated in a certain way to produce an eye, and then we can actually produce faces when we get to the bottom layer. Okay? So notice that we're actually getting successively abstract. We're learning things about our images, or our inputs, whatever they are. So this network is called a deep belief network. A deep belief network. It's basically a stacking of restricted Boltzmann machines. It's a stacking of restricted Boltzmann machines, starting with just ones and zeros, if you will. Okay? And once we have such a network, we can do all kinds of interesting things with it. Okay? So for example, we can take an image and we can basically fix it in place. We can clamp it, okay? And then we can see how atoms in the next level activate, which represent, again, sort of parts of edges and facial features and so on. And then how atoms in that level will activate. That might be sort of, this edge and this edge make sort of part of an eye or something, and how that last level activates and so on. Okay? And what we can do is if it's trained with enough input images, the deep belief network can actually learn to recognize common elements in those images. In other words, it's going to say, you know what, I saw a million images that I was trained on, and there was a thing that looked like a cat face in all of them, okay? And this node, or rather that atom, might be associated with a cat face. And in fact, if you look at Google's Deep Brain, I forget what they called it, they actually, without telling the system anything about what a cat looks like, it actually learned that this neuron represented a cat, and if you were to actually take this neuron and sort of propagate back up, it would actually show you a cat on the visible layer. It learned this without being told what a cat was or anything else, because there were so many cat videos they trained the system on, millions of pictures of cats in YouTube videos, that it actually learned a sort of a iconic picture of a cat. Okay? Without ever being told what a cat is. Okay? And by the way, it's sort of interesting. If you basically take this network and you let it vibrate between these two layers, so just let it vibrate, right? On, off, based on those weights. And after a while vibrating, you then propagate that back up, you're going to get stereotypical images that sort of come from your distribution of images that you train the system on. It'll actually daydream cats and dogs and trucks and whatever people have, beaches and whatever people have trained the system with. In our case, it would be happy faces, sad faces, sort of really happy faces, and so on. Okay. Now, with a bit more coding, we can actually determine which atoms in the bottom layer activate for each type of input image. Okay. So, for instance, we can say, oh, all the images that have a happy face have these two atoms activated, and therefore this is associated with happy faces. You could use machine learning, other techniques on this in order to say, ooh, I just saw a picture of a happy face, right? And we could build a classifier. So basically, after pumping in millions of images, and the system sort of gets an intuitive understanding of the regularities across all the images, all the edges, and so on, we can then pump in all those images again, get the bottom outputs, that bottom hidden layer, and that will be a description of every image. It might be, oh, a person, that might be hair, that might be a nose curled down, that might be a face, mouth curled up, and so on. And basically, we can actually compute, if you will, what combinations or types of combinations would be associated with happy people or sad people or trucks or cats or whatever. And now you could pump in an image potentially and recognize, ooh, there's a cat. Okay? Now, you can also deal with noisy inputs. Okay? So what if you have, for instance, a signal like somebody's voice, which is a little bit noisy. There's noise in the background, or you have an image which is sort of noisy. It's grainy. Okay? So imagine I pump in an image. It looks sort of like a face. Well, guess what? Because most of the atoms are there, that's going to tend to activate the next layer in the same way. So we're going to activate the same atoms that would be activated generally if it were a proper image. We're going to propagate that down, propagate that down. We're going to say, ooh, I was just presented with a picture of a happy person. And then you could propagate that. Well, you can sort of recognize things that are noisy. In other words, if it's close enough, the atoms at each successive layer are going to activate, and we're going to be able to identify that, in fact, we saw something that we recognized. So it doesn't have to be perfect. The inputs don't have to be perfect. Or, for example, we can reconstruct. So imagine I take a face like this, okay, which is sort of half there, and I propagate down, I clamp it, and I propagate down, propagate down, propagate down, and then I propagate back up. I say, ooh, okay, well, this is what activates. It looks a little bit like a happy person. If I propagate it back up and then see what actually is visible on the visible layer, I can actually get my original happy face. So it's going to say, ooh, I know what that looks like, and I mostly activated, and now I'm going to activate back up. And it might be a little bit more complicated. You might propagate back down, vibrate around here a while, doing Gibbs sampling, and then propagate back up. Okay? And you'll see this actually works. It's very interesting. You can give it a partial image. That actually puts it in a particular state which is close to what it wants to be in. And then if you vibrate it a bunch, it'll go back into the right state. And you can use this to detect anomalies, which is interesting in computer security. That's what we're interested in this for, at least one thing. Okay? We can take an input image like that, okay, and propagate it down through our network. Now remember, this network was trained on happy faces. The only things it's ever seen are 3 happy faces, let's say. Okay? But we'll take this image that basically doesn't look at all like a happy face, and we'll propagate this down, and we'll see what atoms activate. Now remember, these weights are associated with images of faces, not with that crud of atoms there. But we'll propagate it down, okay? And we say, oh, it seems to be there's a nose in this input image, and it seems that there's like a mouth in this input image, because it doesn't know, all it knows is faces, so it's just sort of getting these atoms activated, and it basically goes all the way down. And then if we propagate back up, we say, okay, well, let's clamp this down, and let's propagate up. Well, those atoms would activate, and those atoms would activate, and guess what? It says, oh, that looks like a face and part of an eye or part of a nose or something, right? This is what it thinks it saw. Because as far as it's concerned, it's only seen images of faces, and this is about as close as it can get to that, basically based on its activations. Now, if you compare this image to this image, and they're wildly different, it means the images are anomalous. In other words, the image you presented it does not look at all like what it was trained on. It's nothing like what it's seen before. On the other hand, if I presented it with something that looked mostly like a happy face and it came back with something that looked mostly like a happy face, I could say, ooh, this is something it knows about. And so you can use this for computer security. You can measure, for instance, normal activity on a system. And if you see abnormal activity and you pump it through one of these systems, then you would expect to see that the output, if you pump it back up, will look not at all like what the input would be. Okay, and we can compare the input and the output images and say, wait a second, they don't look at all alike. But if you happen to pump a face in there, it would look very much alike. Okay, so if our output significantly differs, then this is a strong indication of unusual input. And so for those of you who speak machine learning, notice I didn't classify anything. I didn't have to have any supervised learning. I didn't have to say that this is a picture of a cat or a happy face or anything else. I literally pumped in images. I said, network, learn how to optimize for this image. Learn how to vibrate to this image by picking a set of weights, and that's all I did. And it figured out the rest. Now here's the kicker. So we literally pumped in raw data into our restricted Boltzmann machines. We did it multiple times on multiple layers, and it figured out the rest. These gradient descent algorithms figured out the rest. Most traditional machine learning approaches require an engineer to do an extensive amount of feature extraction. So they basically require you to say, oh, I'm building a network on faces. Every face has an eye, a nose, and a mouth. So I'm going to go and build an eye detector, and I'm going to have a 1 on an atom if there's an eye, and another 1 if there's an eye, and 1 for a nose, and so on. You don't have to do any of that. The system just figures it out. Okay? So we don't have to do any of that. It just figures out the information. So what are some recent wins? We're almost done here. So Baidu recently announced a deep learning system, deep speech, that used massive amounts of data, okay, to achieve roughly a 29% improvement in speech recognition with 2 weeks of work. So they literally took some existing components off the shelf, they built a system, and they pumped in 100x more data than ever had been pumped into a machine learning system before, or a deep learning system before. And these other systems here from Apple and Bing, Google, and so on, they have They are very complex systems, millions of lines of code that are detailed. They transform the input signal in different ways. They look for phonemes and phonemes? I don't know, phonemes, there you go. Okay, they do all kinds of crazy stuff. This system was literally what I showed you, literally converted into a frequency domain or whatever it was. They trained a bunch of restricted Boltzmann machines, multiple levels deep, actually used what's called a recurrent neural network. Okay, and they actually achieved, error rates. Look at that error rate on clean. No, clean means there's not a lot of background noise. Clean speech recognition, about 6.56% error rate. Okay, versus, for instance, the best before was 6.64, and that had lots of hard-coded, very specific stuff in it. Okay, in noisy environments, okay, they achieved a 19% error rate, just pumping in data in this type of approach, versus all the existing systems that are really, really hand optimized to solve this problem, and they did it in 2 weeks. 2 weeks. Microsoft Research recently published an image recognition result that achieved 4.94% on the top 5 error rate. I don't know how many people are familiar with ImageNet. Okay, this is good. This is all. I'm getting to the right group of people, hopefully. So there's a database of millions of images, or I don't know exactly how many images. It's called ImageNet, and they're all classified. So somebody actually went through and did a classification of every one. There's a mite, there's a person in a convertible wearing a straw hat, okay, and so on, okay. And the goal of this, it's a competition, is to basically take a subset of the images and train on them. For instance, build those restricted Boltzmann machines we talked about, okay? Take the rest of the images and see if you can guess what's in those pictures. Now, 5-10 years ago, we would have looked at this and said, there's no way a computer system could figure out, do computer vision and figure out what's in an image. I remember when I was taking computer science at UCLA, they had pictures of blue balls on gray backgrounds, and it was difficult to even figure out it was a ball with the vision system, right? These systems, okay, basically, when we say top 5 error rate, there are 5 guesses that the system is allowed to give for each image. Okay, so for instance, the Microsoft system can say, I think it's these 5 things. These are my 5 biggest guesses, my 5 highest probability guesses. And if you get one of them right, okay, then you're doing okay. Microsoft achieved a 4.94% error rate on this, which means that 95% of the time, roughly, the guess that they made was in one of the top 5 guesses was right. Okay, they guessed it was a mite, and they guessed it was a container ship, and they guessed it was a motor scooter 95% of the time. And guess what? The established human error rate is 5.1%. This actually does better than humans using deep learning. Yes?
On the speech result, how many of those 4 top guys there basically shared nuances at the back end?
I don't know. I can't tell you that. That's a good question. Because maybe there's a reason why they all did this.
That's right.
Yeah, I don't know. I mean, the results are different enough that you would guess that at least they did some differences in the speech engines.
Either pre or post processing.
Yeah, I don't know. That's my best answer, and I'm sticking with it. Facebook, which is actually an older result, but Facebook actually, they built something called Deep Face, which did a little bit of processing. They actually took a face. If they only had half a face, they would actually use the half they saw to project a symmetric copy of the face for the other side in order to produce a face from the front. And then they trained their system on faces. It achieved a 97.25% effectiveness rate of saying, given faces that it's been trained on, given a new face, identifying whether who it belonged to. Okay. The current sort of human level accuracy is 97.53%. So we're getting really close to this stuff, and this doesn't require a lot of crazy. Pre-processing. They did some, but these other results are, very, very simple. Okay, so what are the catalysts for this? Why have we seen this explosion recently? We have, we had, Hinton and so on, Sosnowski doing their work in the mid-2000s, but why have we seen an explosion recently? Well, in 2006, as we said, this really, Geoffrey Hinton really kicked off this revolution, I would say. Okay, he wrote a paper, a fast learning algorithm. For deep belief data, for deep belief, I can't read the last word there. I don't remember the title, that's embarrassing. Hold on, let's see. Nets, deep belief nets, okay. And this basically described effectively using RBMs in this way, okay? And doing what's called greedy layer-wise training. So what's greedy layer-wise training? This is where we train one RBM at a time. So we train one RBM, we use the gradient descent algorithm, so the weights, okay, cause the visible plane to display what we want more frequently than the things that we don't want. And once they did that and they got these hidden layers defined, they went one more layer deeper, and they went one layer deeper, and so on, okay? Now, why was this actually really interesting? Because before, we had neural networks that look like this. We've had neural networks that look like this for 30, 40, I don't know, 50 years, a long, long, long time, multi-layer neural networks, okay? But nobody could train these neural networks effectively all the way through, okay? And there are various reasons for this. There are mathematical reasons, like for instance, when you do backpropagation and you actually try to compute these weights, there's errors that basically explode in the network as you go in, or actually diminish. Your deltas as you change the weights actually go up or down, and you end up not training the neural network effectively if it gets too deep. So what Hinton's contribution was is he said, hey, let's do greedy layer-wise pre-training. Let's train a layer at a time. We'll get that right. And once we get that right, we'll do that and get that right. And once we do that, we'll get that right. And once we do that, we'll get that right. And then guess what? You can do one pass through this whole system and optimize it even more because it's in the ballpark. Now that we've trained each little layer, it's in the ballpark. And this was what kicked everything off, because previously we just didn't have the computing power or the math in order to do this. And the other thing that came since then really is huge computing power increases. So GPUs, these graphics cards that we use for mining bitcoins and playing video games, are really, really good at deep learning algorithms, because deep learning algorithms are primarily using, matrix algebra, like linear algebra, right? And so GPUs are literally thousands of times faster than traditional CPUs. And so we can do far more calculations and for a very cheap price. And so what this allowed us to do is it allows us to optimize bigger networks that can actually process more data, solve more interesting problems. Okay? And the other thing that really was an accelerator is the internet has provided so much more data. Crowdsourced data, whether it be from Google searches or images you put on YouTube or voice chats you do on Facebook or whatever it happens to be. Actually, I don't know if Facebook mines that, but lots of this data is being mined. And if you just pump in huge amounts of data, data is king or queen. Okay? The more data you have, you can train these systems to do virtually anything. And that's what we saw with the Baidu result, right? Just by pumping in 100 times more data into a traditional system, it was able to learn these regularities. Okay? So if you combine, this sort of intuition here that we can do a layer at a time to start with, more computing power, well, guess what? Now, and there's a debate about this, it's not obvious that layer-wise pre-training, where we actually do a layer at a time, is the best way to solve this problem, because we have so much computing power now, and we have some algorithms that we can actually run because we have so much computing power, that we can actually train these networks straight through. Okay? And so there are advances in machine learning. For instance, how do we initialize the weights? If you initialize the weights to all kinds of random values, then the network actually may not converge on the right set of weights to actually maximize the probability of things vibrating upright. But if you initialize the weights in special ways, you can actually cause the system to actually get closer to the optimal configuration. And so, coupled with better computing power, the algorithms that we couldn't have used before, because they were too expensive, for instance, we knew how to do a lot of these things, we can now effectively train these networks straight through, not one at a time, one layer at a time, but just all the way straight through. And in fact, some of the best results are training networks straight through, just using some of the newer results, or newer approaches, and some old approaches that weren't feasible before this computing power and data were available. Okay? So right now is actually it's a Hatfield and McCoy war, a big Indian versus little Indian war, of whether you do layer-wise pre-training or whether you train the thing all as one big network, multiple layers deep. So one last thought, and you see them on the brain now. We're literally done in 1 second here. Have you ever thought how amazing visual memory is? I mean, before I started studying deep learning, and again, you can tell I'm an amateur, right? I mean, this is not my area, but I think this is the single biggest, most interesting result. I was wondering, how can I remember images from when I was literally 5 years old? Because all of us remember things from when we were young. We remember things from yesterday. We see a menu, we remember things from it. We see a dish or a birthday cake. Do you think that our brain basically stores high-level snapshots, like literally multi-pixel snapshots? Sorry, let's do that again, of cats. All the cats you've seen on YouTube. Do you think that your brain is literally storing like 1,000 by 1,000 pixel images somehow in your neurons? Probably not, right? Maybe not. Maybe what's happening is that we have visual receptors that are finding some simple features. Okay? We have another layer of neurons that are identifying regularities across the things that we see, right? So, ooh, a cat, a cat, a cat, a cat. All of them have eyes that look like this and whiskers that look like this. Oh, regularity, regularity. We have a set of neurons, a layer behind, or maybe our visual neurons. And then another set of layer of neurons behind that. Ooh, two eyes are together usually with cats. Oh, okay, that neuron's going to activate for two eyes. And what if the encoding of memories is actually a multi-layer, okay, multi-layer approach, just like we saw with these Boltzmann machines. In other words, you have some cat neuron in your brain, or maybe a set of cat neurons, okay? And when you see a cat, all of the images, all the elements of the eyes and so on are going to activate that cat neuron, okay? And when you encode a picture in your brain, you're not encoding a 1,000 pixel by 1,000 pixel image or 4K by 4K image. You're encoding, hey, that picture that I remember had a cat in it and it had grass in it. That neuron activated, and we'll maybe have some connections between them. You're encoding very low, sparse information, very little information that can represent the original image that you saw. So an image can actually be stored potentially with very little information if you already have built these structures in your brain that represent these regularities. Okay? And think about when you daydream. What do you daydream? You daydream the things that you sort of know, you've seen before. You daydream the stereotypical cat. Okay? Or maybe somebody's face that you've seen many times. So this could explain why, given a memory cue, you can suddenly remember a whole image, right? Remember I showed you, I could give it a partial image, and because I'm going to activate those atoms that are related to that image, it goes all the way down, boom, I activate some neurons there, and then I process it back up, and I say, ooh, I remember what that was. Right? That would explain that. Or when viewing a partial image, your brain can visualize the rest. If I see part of somebody's face, I can visualize what the rest of their face looks like. Okay? Or when you see something unusual, your brain knows it immediately. When you hear a pun, you know there's something funny about that pun. Or when you see something, an image of a cat on the moon, you're like, wait a second, cats are never on the moon. I don't have any neurons that represent a cat on moon rocks together. But I do have neurons with a cat on grass together. Okay? So you can recognize anomalies. You can picture them in your mind's eye. And after seeing hundreds of cats as a kid, okay, pictures of cats, cats walking down the street, cats on YouTube, for people who grew up in the YouTube era, and you never knew what they were called. You just saw cat, 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 cat. I've seen all cats from every angle. And then suddenly your mother or father says, that's called a cat. And you instantly know what all cats are. Because now you've just associated a term, a vocalization, with that mother neuron of a cat, or mother neurons, and you now know what cats are. Think about that. Because you're not associating the term cat with every high-resolution image of a cat you've ever seen through your visual cortex. So in conclusion, deep learning is a machine learning technique that works by learning multiple levels of abstraction about its inputs. Okay? The regularities, the things that are common across its inputs. Once a deep learning system learns the inherent structure of its inputs, you can use it to classify items, to reconstruct partial inputs, to detect anomalies, to search for related items. We didn't even talk about that, but you can actually use this to search, right? Hey, find me all things that look like this picture of a cat on the moon. You can do that. Or you can just daydream with it. These networks, literally, you can let them vibrate. This was the most fun I had when I was building the system. I built these restricted Boltzmann machines, and I would let the system vibrate, and I would actually I was doing this on the MNIST database, which is a bunch of numbers that were handwritten numbers, and the system would actually just dream up numbers that it had seen before. And they didn't look like the numbers they were trained on. They were sort of close, but not quite. They were, sort of combinations of numbers that it had seen before. Just like you daydream, these systems daydream. They vibrate up, and they will show you on their visible display what they think. And finally, the engineer doesn't have to do lots of pre-processing to apply this to problems. You can literally pump in raw data in many cases and get results. And finally, this is a sales pitch if you enjoyed this talk. I just finished authoring a novel. It's going to be available on all the major sites on April 14th, and all of the funds are going to charity. So take a look, enjoy it. I think you'll enjoy it. It's a cyber thriller, techno thriller, and it's for a good cause. So thank you.